Hi guys, and welcome to Unit 47. In this unit, we explore basically moons of the solar system, and we take them basically for most of the part are the outer moons, because that's really the outer planets moons, that is, because that's where the moons are, with the exception of the Earth's moon. So moons were first discovered, among other things, by Galileo in the early 1600s, where he noticed that there are 4 moons that orbit the planet Jupiter, and hence the name Galilean System, because of the fact he's the one who's discovered them. And then after that, we started to discover that there are far more moons in the outer planets than those 4 moons. So in terms of size, the solar system moons, some of them are larger than Mercury, than planets, so they are big. Okay. The biggest moon in the solar system is Ganymede, and that's the third furthest moon from Jupiter in terms of big moons, because as I was saying, Jupiter has a lot of moons. Then after that comes the moon of Saturn, namely Titan, and the third size basically moon in the solar system goes back to Jupiter moons, Callisto. So there are basically Ganymede, then Titan, then Callisto. And then the 4th moon also, just to show you the importance of the Galilean system, is actually Io, which is a moon of Jupiter also, that was discovered by Galileo. So 3 out of the 4 largest moons are in Jupiter. Then the 5th moon, actually, in terms of size, is Earth's moon. And that's why in the previous units that we discussed in Unit 39, we took the Earth's moon as a topic by itself, and we discussed it in detail. Among other things was the fact that the Earth has it, because it's a big moon. I mean, it's the 5th largest moon in the solar system, so it's a big moon. And then just to emphasize the idea that Jupiter has really some of the largest features in the solar system, the 6th largest moon is also a Jupiter moon, namely Europa. So just to give you an idea how the Galilean system fits in. I mean, it has the biggest moon, it has somewhere in the 3rd moon, and it also has the 4th moon and the 6th moon. So this is basically the system. Obviously, Jupiter has a lot of moons. And here is the point that we want to emphasize. There are 2 types of orbits for these moons. There are the moons who are basically coplanar with the planet itself, meaning that they are on the same, more or less, the ecliptic plane. Those, as opposed to the moons that are not on the same plane, they could have irregular orbits, basically. So you have regular orbit moons and you have irregular orbit moons. The theory is that those who are on the same orbit must have formed during the same time when the planet has formed. They form in the neighborhood of that planet, and basically they get stuck there because of the force of gravity. Now, the moons that have irregular orbits, namely their orbits are making big angles with respect to ecliptic, number 1, or they have an eccentricity that is too high around the planet, not around the sun. Those, they must have been captured objects, basically, objects that they have, these moons have captured. And then this planet has captured. So this is basically the theory in terms of how this moons formed. So the formation can go anywhere between the 4 models that we basically explored when we talked about the Earth's moon. So just to give you a refresher, so you have the ones that are captured, the ones that formed in the neighborhood, and the ones that were probably ejected due to some collisions with the planets, and maybe a combination of both, that after a collision, like the case of the Earth's moon, materials get ejected and then coalesce later on to form the moon. So this is some of the things in terms of the moons. Another feature that is also important for this moon, and that is their structures. For the most part, maybe in their cores, there could be some sort of metallic and maybe also silicate, namely rocks, That's because of how that planetism was actually to form in the begin with. But for the most part, those moons are icy objects. Namely, you have solid ice or other things in their outer layers. Some of these moons have actually internal structure that shows that they have salt water inside their moons, and the water cycle actually, or the water, I should say, temperature is the one that is driving their geology in terms of volcanic eruptions, but not that of the one that we know it, at least on Earth. A lot of these moons are actually, they are in some of the closest ones, at least from their own host planet, they're tidally locked to their own planet, just like the case for the Earth and the Moon, meaning that they face the planet in only one side. However, because you have so many moons, you could have a resonance in this case. So what I mean by that, let's say, for example, I take Io, which is the closest moon from Jupiter. At sometimes Io is on one side, and of course, Jupiter is always on one side of the Io. So you have Jupiter, but on the other side, you could have Europa. You could also have, Europa is the closest object from the moon itself, from Io, or you could have Callisto, or you could have Ganymede, or Ganymede and Callisto. So now, in that situation, where Io is on one side and everything else, including the other moons, are on the other side, they would be pulling on it a lot stronger on this side. In some other situations, because of this resonance, what I mean by resonance is that after a certain number of rotations, the other one completes also an exact number of rotations. And that ratio is basically a fractional ratio, namely a rational number, ratio of two integers. So in that case, after so many rotations, the other one completes the other and becomes on the other side of the moon. So here is the situation. So the gravity now weakens on this side, and the moon basically relaxes a little. At some other point in the cycle, you will have Io on one side, of course, Jupiter on one side, and all of the other three moons basically on the other side. And they're big moons, as I was saying before. So Europa helped with Ganymede, helped with Callisto to pull on Io on the other side. Of course, Jupiter is always pulling on it. So the force of gravity tightens when everybody is on one side and relaxes when all the moons are on one side and Jupiter on the other side. So because of this, there is kind of, if you take dough and you start to working it out, so sometimes you stretch it and sometimes you push it back, that leads to heating inside of those planets. That's why, I mean, those moons, I'm sorry. And that's why Io is so active in terms of volcanoes, because of the internal heating that it goes through. And this example is just for Io, and then other examples also for other moons of those planets because of similar situations. So this is basically the idea in terms of how the moons look like. Now, some of these moons, they have geological features indicative of some sort of plate tectonics. And I'm thinking in terms of Miranda, I think, has those features. So you have so many features in there. Some of them are actually covered with what appears to be dark matter, which is probably soot from either the collisions or some other object, other things, or volcanic activity from the rocks that are actually in those moons, and so on and so forth. And so this is in terms of structures, in terms of positions, in terms of main features. Also, some of this, the point in here related to these moons that we want you guys to focus on is the fact that all of these outer planets, they have rings in them, okay? So if you look at Saturn, of course, has the biggest rings and the biggest structure. When Mr. Galileo looked at it, he saw the shape kind of weird. He didn't really resolve the shape until Huygens later on resolved that those are actually not the planet by itself, and the ring structure is outside and it's super thin, okay? It was actually later on when we actually started to discover that those they must be a small icy object for the most part. And if you combine all of them together, they amount to probably a small moon. So it's not like they are big in terms of mass, but they're spread over a big region. If you take, for example, the case of Saturn, you have them in they bunch together in groups. You have the A basically ring, and then you have the B and the C, and between them there are gaps, okay, like the famous Cassini division. So those are some of the features of this of the outer solar planets. Again, we were able to discover that even Jupiter, Uranus, and Neptune also have rings, not just Saturn. And they're similar structures. Those gaps usually are driven by shepherd moons. So there are tiny moons in there that basically interact with the ring itself, and basically starts to pull and push on the objects and creates a gap between them. So this is some of the features of the outer planets, and they're basically satellites. So this is the topic of Unit 47. Another point that you need to be aware of the fact that how do rings to form in the first place is that if a moon gets very close from the planet, and because of the phenomenon I discussed earlier, namely tidal heating and tidal interactions, the moon starts to fall apart actually, and basically break apart into tinier and tinier objects. And that limit is about 2.5 or 2.44 the radius of the planet. So once you are within that range, the force of gravity becomes so intense at that point, and the heating and the tidal basically forces become so gravitational tidal forces become so big at that point that the moon starts to fall. Initially, it starts to stretch like an egg, and then it's going to fall apart. That limit is called the Roche limit. So this is basically the points that you need to be aware of in this unit. And I still follow up with another discussion on Unit 48. So I'm not sure, honestly, at this point, if we have to probably put that for the next week's assignment or not. It depends on how I'm going to structure, especially given the fact that there are a lot of problems related to the assignments this week. Thank you.